Hello and welcome to Void Electronics. In today's video I want to talk about the most important theoretical aspect in electronics, and that is Ohm's law. I know there are countless videos about this topic online, however I will do my best to make this one different, by doing it as intuitive as possible. To make it as intuitive as possible, I will start by talking about some theory, then I will show you some basic experiments, and then at the end I want to show you some exceptions or situations where Ohm's law doesn't apply exactly as you'd expect. Simply speaking, Ohm's law states that if you have a resistor, the voltage drop across the resistor is directly proportional to the current through that resistor. And this ratio between the voltage and the current is called the electrical resistance. If you think about it, this concept is really intuitive because a resistor resists or opposes current flow. So that means that the higher the resistance, the lower the current for the same voltage drop across the resistor. So one of the simplest problems that you can solve using Ohm's law is to find out the current through a resistor based on the voltage and the resistance. Let's start by drawing the schematic for this problem. So I'll start with a voltage source of 10 volts. Which is connected to a resistor with a value of 1 ohm. And now we can apply Ohm's law to find the current through the resistor. So the current is voltage divided by resistance. So in our case, since we use some simple numbers, it is 10 divided by 1. So the current is 10 amps. An important thing to note here is that Ohm's law has 3 forms, so it would be a good idea to just memorize one and find the other ones on the spot. So if you want to find the voltage, voltage is current times resistance, and the resistance is voltage divided by current. And also, if you want to build this experiment in practice, then you need to take into account the power as well. That's because resistors have a certain power limit. In this case it is 3 watts. So you have to do the math and make sure that for your resistor you don't exceed this value. So to find the power, there is a formula for this as well, which is P equals V times I. So you can simply multiply the voltage and the current to get the power. In our case it is 10 multiplied by 10, so we have a power of 100 watts. So our resistor has to be at least a 100 watt resistor to handle this power. And also keep in mind that the 3 formulas for Ohm's law can combine with the power formula into 12 different formulas for finding one variable if you know the other 2. So you get a table that looks something like this. However, I wouldn't recommend learning this by heart. Instead, I would recommend memorizing one of these and this formula for power and finding any other form on the fly. That's because if you think about this, once again, this is really intuitive. So as I said in the introduction, the larger the resistance, the lower the current for the same voltage. So this is the heart of Ohm's law. So if you remember this, then you probably remember this form, and you can get any other formula by doing some basic math. And now let's test all the math by building this experiment. First of all, let's start by measuring the resistor to make sure it's a 1 ohm resistor. To do this, since we are working with a really low value, I would like to compensate the resistance of the test wires. So to do this, I will connect both of them to one terminal of the resistor and just cancel out this value. And now I can move this probe to the other terminal of the resistor, obviously with the resistor disconnected from the power supply, and now we get a value which is close to 1 ohm. So I've connected the resistor to the power supply, and now we have to set the power supply to 10 volts and read the current. So as you can see, at 10 volts we have a current of about 10 amps, which is exactly what we expected. However, we also have some differences here, so we can see that the current is slightly lower. And if you're wondering where this difference comes from, well, it's mainly caused by the resistance of these wires. So ideal wires would have 0 ohms, however there is no such thing as ideal wires. So you have a certain voltage drop on these wires which impacts the measurements just a bit. So to demonstrate this, I will measure the voltage that we have at the output of the power supply, which is about 10.1 volts. Let's make it closer to 10 volts. Okay, I would say this is good enough. So we are at 10.0 volts. And now let's measure the voltage that we have across the resistor. And you can see that we are at around 9.9 volts. So I have about 100 millivolts of difference. And this difference is the voltage drop on the wires, which is something that we can also measure. For example, let's take the negative wire. We can connect the multimeter in parallel to the negative wire, and we can simply measure the voltage drop across this wire. So we have around 64 millivolts of drop just across one wire. And we can also measure the voltage drop across the other one. It should be similar, so yes, it's around 60 millivolts. And by adding these values, we get the difference between the voltage that we read here and the voltage that we actually get on the resistor. So if you paid attention to this experiment, you probably noticed that for any voltage, the current is basically equal. So for 2.8 volts, we have 2.8 amps approximately. For 4.1 volts, we have about 4.1 amps, and so on. So make sure to watch this video until the end to see why this is important, because not all devices behave the same. Just for fun, let's see how we can change this ratio between the voltage and the current. To do this, we have to use a different resistor. This one is 20 ohms, for example. Let's just connect it to the power supply and do some math first. So for 15 volts, we expect a current of 750 milliamps. As you can see, the current and the voltage are once again proportional. However, the ratio is a lot different. And for 15 volts, we get here 0.8 amps, which is close enough to the 750 milliamps that we calculated. Unfortunately, things are a little bit more complicated with AC circuits. For example, I have here this variac which will run at 230 volts. But before doing this, let's test its resistance to see what we get. Its resistance is a little bit more than 1 ohm, so let's do some simple math here. Let's assume that this variac has a resistance of 1 ohm. So by plugging it in at 230 volts, we should get a current of around 230 amps, which gives us a power of around 53 kilowatts. So basically it will look like a dead short. Let's see if that's the case. To test our theory, let's just plug in the transformer and see what happens. Worst case scenario, it will just blow a fuse in the other transformer. But before doing this, we have to talk about some safety aspects. This experiment works with lethal voltages, so you should not try this at home. If you want to try this experiment at home, you do so at your own risk. With this in mind, let's keep going. So far so good. And at 220 volts we have a current of around 3 amps, so it is much lower than the 230 amps that we calculated earlier. So to analyze what happened in our experiment, we have to talk about some concepts. First of all, let's talk about Ohm's law in AC circuits. Well, in AC circuits, Ohm's law applies a little bit differently. So I equals V over Z, where Z is the impedance. The impedance basically extends the concept of resistance for AC circuits. So the impedance is a complex number that equals resistance plus Jx, which is their reactance. So what it means is that for certain circuit elements like capacitors and inductors, we have a certain reactance, which means that the current and the voltage through that element is out of phase. For example, for an inductor, the current is out of phase by 90 degrees with respect to the voltage, and the current actually lags the voltage by 90 degrees. For a capacitor, we still have a 90-degree phase difference, but the current actually leads the voltage. And for a resistor, the voltage and the current are in phase. So let's get back to impedance. This is reactance. R is the resistance, just like before. And Z is impedance. And they are all measured in ohms, by the way. If you're wondering what J is, well, J is the imaginary unit, and J squared equals -1. And that's because in electronics we use J instead of I, because we don't want to create confusion between this and the electrical current. And now let's see what the impedance looks like for some circuit elements. For a resistor, ZR equals to R, so it's simply the resistance. That's because the resistor is not reactive, so the current and voltage are in phase. For a capacitor, things look a bit different because the capacitor is reactive, so its impedance looks something like this. It's 1 over J omega C, where omega is 2 pi times the frequency. And for an inductor, we have J omega L. An important aspect about this is that the impedance for reactive elements depends on the frequency. So for a capacitor, the larger the frequency, the lower the impedance, and for an inductor, the larger the frequency, the larger the impedance. And in our case, since we are looking at the inductor current without looking at its phase with respect to the voltage, we can simply work with the absolute value of the impedance, which looks something like this. It is simply omega L. So going back to our variac, its impedance Z equals to V over I, Z equals to 220 volts over 3 amps, so Z equals to 73.33 ohms. First of all, let's make some comments about this value. If you remember, we measured the resistance of our variac with a multimeter, and its resistance was around 1 ohm. However, at 50 Hz, we can see that the value is much larger. It is about 73 ohms. So to understand why that is, you have to look at the way the impedance varies with respect to frequency. So at DC, the frequency is 0, which means that omega is also 0. So the impedance is also 0, because you have 0 multiplied by whatever inductance the inductor has. This applies to an ideal inductor. However, for our real inductor, we had a DC resistance of around 1 ohm. However, at a larger frequency, for example 50 Hz, the value of the impedance changes, and according to this formula it gets larger. And that's why we see this value here, and that's why our variac didn't blow the fuses. And by the way, since we have the impedance at 50 Hz, we can calculate the value of our inductor. So L equals the absolute value of ZL divided by omega. L equals the absolute value of ZL divided by 2 pi times the frequency. L equals 73.33 divided by 2 pi times 50 Hz. And L equals 233 millihenry approximately. Other exceptions from Ohm's law are non-linear circuit elements, and one such element, believe it or not, is the incandescent light bulb. Let me show you what I mean by that. By looking at the parameters of this light bulb, we can see that it's supposed to run at 235 volts and it has a power of 500 watts. So by doing some simple math, the resistance of the light bulb should be around 110 ohms. So let's just measure it before anything else. And as you can see, the resistance is around 9 ohms, so it's more than 10 times less than what we calculated. Let's see why that is. So the first thing to do is just to power it up and see if it draws the right amount of power. So let's do that first. And as you can see, at 235 volts, it draws about 2 amps. So it draws the right amount of power, which confirms the fact that the filament is around 110 ohms. However, we still have a huge difference between what we measured with the multimeter and what we observed based on the current and the voltage. So to get a second clue about this, let's just repeat the experiment and measure the resistance of the filament right after we turn the light bulb on. Now let's quickly move it to the multimeter. And as you can see, the value is a lot different. It started at around 20 ohms and it keeps going down. And the fact that it goes down is also a clue about what I'm trying to say here. So the explanation for all this is the positive thermal coefficient of the filament. The filament is probably made out of tungsten, and like most metals, tungsten has a positive thermal coefficient. which means that as the temperature goes up, its resistivity goes up as well. And since the filament is working at a really high temperature, we cannot simply measure it at room temperature and assume that it will have the same resistance at an increased voltage. So taking all these into account, this means that the light bulb is not really a constant resistor. The light bulb is more like a dynamic resistor whose resistance depends on the voltage that powers the light bulb. Another classic example of non-linear circuit element is the diode. We have a diode here that is directly connected to this power supply, and we have this multimeter that helps us read the voltage drop across the diode. So let's see what happens at various currents. So at a few milliamps we already have the typical voltage drop across a silicon diode, which is around 650 millivolts at room temperature. And let's see what happens when we increase the current. Now, at a significantly higher current, or around 100 milliamps, we can see that the voltage drop is not significantly higher, so the rise in voltage is definitely not directly proportional to the current. So we can keep going. At 1 amp we have around 850 millivolts. 2 amps, 870 millivolts, and we can go all the way up to 3 amps, which is the maximum current for this diode. And at 3 amps we have 890 millivolts. So this proves that the diode is indeed non-linear. And if you don't believe me, we can put all these values into a table. So to put all these values on a graph, I tested the diode at various currents. For example, 10 milliamps, 20 milliamps, 50 milliamps, and so on. And for every current, I put the voltage drop across the diode in this column here. And also, for every pair of values, I calculated the resistance in a third column. And this is what the graphs look like for something like this. First of all, let's look at the current with respect to voltage. So as you can see, we get an exponential curve here, as to be expected with any diode. And also, let's look at the resistance with respect to current. So here we have another interesting graph, which proves that diode doesn't have a constant resistance. Instead, the diode has a dynamic resistance which changes with respect to the current through the diode. And now you're probably thinking, well, if only there was a piece of test gear that could make those graphs automatically. Well, it just so happens that I have one, and that is called a curve tracer. We can use the curve tracer to see the current with respect to voltage. So you have the current on the vertical axis and the voltage on the horizontal axis. So if we think about Ohm's law, for a resistor, we should get a straight line, right? Let's see if that happens. And as expected, we get a characteristic straight line that the curve tracer produces for all resistors. So let's see what the diode looks like. According to Shockley's diode equation, we should get an exponential, right? And sure enough, we get a characteristic exponential of a diode. And just for fun, let's characterize an incandescent bulb as well. So I have this small incandescent bulb connected to the curve tracer, and let's increase the voltage and see what happens. So as you can see, the slope changes, which implies that the resistance of the light bulb changes as well. So for small voltages, the line is almost vertical, which means that the light bulb has a really low resistance. And as we increase the voltage, we can see that the line becomes more and more horizontal, which means that the resistance increases. So if you like this video, please give it a thumbs up, and if you're interested in more content related to electronics and programming, please subscribe to this channel because there is more content like this on the way. That's it for now. Bye.